I am the ocean. I'm water. I'm most of this planet. I shaped it. Every stream, every cloud, and every raindrop, it all comes back to me. One way or another, every living thing here needs me. I'm the source. I'm what they crawled out of. Humans, they're no different. I don't owe them a thing. I give, they take, but I can always take back. That's just the way it's always been. It's not their planet anyway. Never was, never will be. But humans, they take more than their share. They poison me, then they expect me to feed them. Well, it doesn't work that way. If humans want to exist in nature with me and off of me, I suggest they listen close. I'm only going to say this once. If nature isn't kept healthy, humans won't survive. Simple as that. I could give a damn with or without humans. I'm the ocean. I covered this entire planet once, and I can always cover it again. That's all I have to say.
Okay, so we're going to start off talking about the ocean. Obviously, it's incredibly important to a lot of what we will discuss here in our coastal marine management class. But also this first bit here, which we'll start on, and we'll see if we get to it all through all this today. But some of the stuff you guys have not covered too well because we maybe haven't had an intro marine bio class or oceanography class, that kind of stuff. So this is my attempt at giving you guys an introduction to the goings-on in our water planet. So this is going to be mostly a focus on the abiotic conditions of things. So again, as with all our stuff, you guys stop me if I'm getting too far ahead or I'm not making sense. What's this? Little teeny blue fleck. Any thoughts as to what that is? The Earth, that's right. So if we zoom in on that thing, that is the farthest away picture we have of planet Earth, taken as Voyager 1 was heading out into space, and then we spun it around and we took a snapshot back just on a whim. Super lucky that we even showed up. It wasn't by design. It was just, this, what the heck, we'll try it. And so this was the basis for a book, Carl Sagan's last book. And really important. I want to read, normally I don't read long quotes, but I just want to read his quote. So here we go. Ready? So this is what Carl Sagan said. He said, he was giving a lecture at Cornell. He said, he showed this photo. And so this is from about 4 billion miles away. And he said, we succeeded in taking that picture from deep space. And if you look at it, if you see that dot that's here, that's home, that's us. On it, everyone you've ever heard of, every human being who ever lived out their lives. The aggregate of all our joys and suffering, thousands of confident regions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilizations, every king and peasant, every young couple in love, every hopeful child, every mother and father, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint, every sinner in the history of our species lived on a mote of dust suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors so that in the glory and in triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of that dot on scarcely indistinguishable inhabitants of some other corner of that dot. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds, our posturing, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dusk. In our obscurity and all the vastness, there is no hint that help will come from elsewhere to save us from ourselves. It's up to us. It's been said that astronomy is humbling, and I might add also a character-building experience. To my mind, there is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly and compassionately with one another, and to preserve and cherish that pale dot, the only home we've ever known. That dot is blue for a reason. That dot is blue because there is water here. We are a water planet. For reasons that are not entirely clear to me, the environmental movement for a long time has been called the green movement. But really, a healthy planet would be not just green, it would be mostly blue from our ocean and the effect of water vapor on sunlight in the atmosphere and stuff. Water is what makes us unique, at least in our nearby astronomical neighborhood. Water exists elsewhere. Water exists on Mars, despite for decades people were saying, I don't know if water exists on Mars, I don't know. It did, and it does. So for example, here is an image from 2005 showing in this shadowed, what had been for the most part shadowed crater, we actually see what we now believe to be frozen water. And this is, this is a decent amount of water, but it's not covering the entirety of the surface of Mars. As we've continued to explore other places in our solar system, we find that there is water there, right? It's not perhaps as abundant as it is on our planet, definitely not as abundant as it is on our planet, but it is there. So here's another piece of evidence. This comes from one of our Mars exploratory robots, and this guy was trying to scoop up some sediment to take some chemical readings of the composition of the material. And so this is on, so we're essentially looking straight down at the dirt, and we've stuck out a scooper, and the scooper is scooped, and then it's taken that material into a mass spec and is doing some stuff. But this is how we, another line of evidence. So while this isn't a definitive look, it's pretty clear to most observers that this is actually frozen water. So we see that as we first scooped it, there was some water, right? So there's stuff here, and then as the sunlight started hitting it, it started to melt, right? And so we do have water on other planets, but it doesn't do the same thing that it does here because of a lot of, and then also, these crystals here down here melted as well. And then this is over a slightly longer period of many days, and this is taken from a satellite over Mars. But what you see here is you see these what appear to be damp channels forming as presumably this ice is melting and water is starting to trickle, not a Colorado River per se, but nevertheless is trickling down the hillside of this particular crater in 2011. So water does exist elsewhere. The key feature to our planet, if we were aliens coming from afar and just landed, the first thing that we would comment on, even before maybe people and this and that, would be, and the landmass would be the water. So water covers 71% of the surface area of the globe. These numbers I'm showing you here are notoriously hard to get. You'd think they'd be easy to measure, they're actually not. And so slightly different sources put them as slightly different, but we'll just use these as our default numbers. The average depth of the ocean is almost 4 kilometers deep. So I don't get too worried about you guys memorizing a bunch of factoids and stuff. These are key factoids. You should know all of these facts. 71% of the Earth. The average depth of the ocean, about 3.25 kilometers. There are some massive rents in the bottom of the ocean, though, that create these huge canyons and chasms. We usually call these trenches, deep sea trenches. And the deepest of which is the Challenger Deep in the Marianas Trench. And that is almost more than 11 kilometers deep. So there are really deep parts of the ocean, but the average depth of the ocean is still pretty deep on its own, the plain Jane bottom of the ocean. The ocean contains the vast, vast, vast majority of all the mix of hydrogen and oxygen that we call water on Earth. So about 96.5% of all the water is in the form of salt water in our global ocean. The average temperature of the ocean is about 3 degrees Celsius, just slightly above freezing. We first obtained a global ocean. Remember how old Earth is? Right. So for about the first billion years or so, didn't have much of an ocean. But ever since that point, we've had a ocean. So when Harrison Ford said that, you came from me, that was a correct statement. 3.4 billion years this ocean has existed. Much longer than any species, much longer than our species to be sure, much older than our tallest mountains, for example. The biggest geological feature on Earth is in the ocean. It is the mid-ocean ridge that runs, a huge mountain range that runs all across the planet. You can't see it because it's several kilometers underwater. But if we were to drain away the water, it would be an incredibly prominent thing. Part of it we know as Mauna Kea, the place where we have radio telescopes, observatories in Hawaii, on the big island of Hawaii. That mountain is actually more than 10 kilometers high, although you and I perceive it to be a 4-ish kilometer high mountain, because we're only looking at the part that's pushed out of the water and is out into the air. So again, here, this is a slightly different number, right? Everybody has a slightly different way of calculating this, so these numbers go up or down by 1% or so. But suffice it to say, this is a decent breakdown of stuff. Rivers are where humans get their water from, and to an extent lakes, and increasingly in places like California's Central Valley from our groundwater. But note, these are all but a fraction of a percent of the total available water. Most of it is in the ocean. The next greatest reservoir, which is an order of magnitude less, would be the polar ice caps and glaciers such as those in Greenland. So the stuff that you and I have easy access to, that you and I can drink, that you and I can consume, is a relatively small fraction. One of the reasons that Earth is the way it is has to do with the unique chemical properties of H2O. Because of the location in our solar system and distance from our sun, we're able to have all three phases of water simultaneously in existence on planet Earth. That is trippy. That is unusual. It's not all gaseous. It's not all frozen. It exists in all three. And what's determining what phase of, what state the water is in are these two key forces that are pretty trippy in water, pretty amazing. One, we have hydrogen bonds that are acting to hold the different molecules of water next to each other that make them sticky. The countervening force is heat, is energy. They're bumping around, they're vibrating, right? And that's acting to bump into each other and knock us away from each other. So we have the hydrogen bonds trying to pull these guys, pull water molecules and attach them to other water molecules. And then we have heat, which is acting to shove them away from each other. So the state of matter, in the case of water, is going to be determined by these two forces. Ice is when we have the hydrogen bond, the energies from the hydrogen bonds are greater than the thermal energy. And that's going to generate something like this. Now, this is a three-dimensional structure that we're showing in 2 dimensions, but you guys get the idea, right? Stuff is relatively evenly packed in this lattice, this crystalline lattice. So if we take that 3D process and just squish it down to 2D for purposes of me showing you on a flat screen, it looks something like this. The next thing we can do is let's add a little teeny bit more thermal energy. So the liquid is the intermediate state of water on our planet. And that's where roughly the energy from the hydrogen bonds is equivalent to the thermal energy. So the attractive and the dissipative forces are more or less balanced. So what we get there is we get sort of like an ice thing. We get clusters of these water molecules sticking to each other, but it's not that regular lattice pattern. It's not that consistent. Everything is oriented optimally and this and that. It's kind of sloppy. And so we have some of these more stuck together molecules and then some more what we would call free water molecules. The gaseous stage, or the gaseous state, I should say, is when the thermal energy is greatly outstripping the energy, the stickiness from the hydrogen bonds. And in that case, we get water molecules that are not stuck to each other, even a little bit. They are independent players, they're bumping around, and we get a gaseous phase. That very simple physics, that very simple chemistry dictates everything else, almost everything else on our planet. And that has massive ramifications for the critters that live where they live, massive implications for how life is distributed, massive implications for how pollution goes around the planet, how we manage the coast, et cetera, et cetera. So let's talk about some of these things briefly. As a consequence of that stickiness of the hydrogen and all that good stuff, we get properties like this. The first is that water has a high degree of thermal inertia. There's a couple different flavors that we can talk about that. We could talk about water having a very high heat capacity, having a high latent heat of fusion, and a high latent heat of evaporation. It's all basically the same thing. It's just different flavors. The heat capacity is defined as the amount of heat that we need to add to 1 gram of water at standard temperature and pressure to raise that water by 1 degree Celsius. There's only one thing in existence that we know of that it can exist in Earth's conditions that has a higher heat capacity, and that's liquid ammonia. That's crazy. Let me say that again. There's only one compound that we know that has a higher heat capacity, and that's ammonia. So water, which is just this thing that we happen to have been blessed with on our planet for cosmic chance or however it ended up happening, and it's a fantastic, it's a unique molecule. This high heat capacity allows a tremendous amount of thermal buffering and ultimately allows heat transport by ocean currents. So that's why we have, one of the reasons why we have ocean currents. That's why we have these consistent patterns of heat moving from one side, the heat pump of the ocean, taking cold from the poles, taking it to the tropics, taking the warm of the tropics toward the poles, etc. It wouldn't work if water had a different chemical nature. And then related to heat capacity is latent heat diffusion. That's how much we need to take ice and convert ice to liquid. Again, ammonia is the only thing that can take more of that energy before it changes its temperature. And again, this also allows this thermal buffering that we just mentioned. And then again, same idea here. Now we're talking about what it takes, how much energy it takes to convert some liquid water into gaseous water. Same thing. In this case, though, actually water is has the highest latent heat of evaporation, so it beats even ammonia. So water is either the highest or almost the highest in all these things. Amazing that one molecule can do all that. I mean, it truly is. It's one of those things where you never know what you got till it's gone. We grew up with this. We evolved with this. This is our condition, so we expect this to be the case everywhere. It is not. It is a unique aspect of our planet. Okay, so first thing, all that chemistry stuff you guys thought you could forget about after you finished 122. You don't need to think about it. You actually do need to think about it. So first is thermal inertia. Next is this thermal expansion. This is also funky and totally bizarre with water, and unlike just about everything else. Sorry, I'm going to sneeze. I thought I was going to sneeze. Maybe I'm not going to sneeze. Okay. And that is the density of water is going to change with temperature. So the weird thing is that water is most dense at 4 degrees Celsius. Unlike just about everything else. Everything else, the solid is usually denser than the liquid, right? If we had an iron, a chunk of iron, and fired up a big cauldron and had a bunch of iron melting, and we threw a piece of iron into that cauldron, the solid iron would sink to the bottom of the liquid iron, right? And that's just about everything else goes that way, except for water. Think about it. If the solid was denser than the liquid, there would be no ice on the surface of the ocean, right? It would all sink and go to the bottom. So the fact that the solid is less dense and therefore floats above the liquid, that's why we have, all kinds of crazy biology, movement of energy underneath ice caps and stuff like that. Right, cool. We take this physics of the water molecule, and that gives us almost all the patterns that we see when we look around our planet. So let's have a look at this. This is the day-night temperature difference of our planet from compiled satellite imagery. So the colors are just what you would expect. Blue is colder day versus night, and the red is hotter day versus night. But the key point is anything that's not white is different, right? White would be, or very close to the white color, the lightish colors would be very little change between the average daytime surface temperature and the average nighttime surface temperature. So somebody interpret this to me. What's going on here? What doesn't change? Right, the ocean doesn't change. The land changes all the time. There's huge temperature swings on land. And why? Currents, but mostly, right, mostly there isn't any water on land, right? So when you have a rock or a chunk of dirt and the sun's hitting it, it's like, oh my God, I'm getting hot. Or if it's nighttime, it's, oh my God, I'm getting cold, right? The water has, you're right, it has that huge volume underneath it, but also it has that high latent heat of evaporation or all the other thermal inertial aspects, right? So it does not easily get hot. It does not easily get cold. Rocks get hot really easily. Rocks get cold really easily. Water does not. So that means our oceans are really is the home base of the thermal inertia of our planet. So oceans are the great regulator that don't let us get too crazy hot, don't let us get too crazy cold. Let's keep on going with the unique powers of. You guys didn't know you were going to get a cool talk about chemistry and water today. I know you're super excited. I can tell you guys really are liking the water chemistry. That's great. Okay, next let's talk about the dissolving powers of water. Water is often referred to as the universal solvent because it dissolves just about everything. It has the widest, and therefore it's the best dissolver of all known liquids. So if you want to get something that goes into suspension, try water first. And because we evolved in the ocean, you and I and our ancestors evolved in the ocean, we've sort of we've taken along seawater. So you guys are seawater, basically, right? We're bags of seawater walking around, more or less. And that water is both solvent and also the basis for a huge range. Almost all of our biological chemistry is associated with some aspect of this. And not only the biology of you and I and of the paramecium and all this kind of stuff, but also a lot of the basic geochemistry that we observe across the surface of the earth, weathering of rocks and this and that, is the way it is because of the dissolving, eroding powers of water. What else do I want to say here? Yeah. So I'll just keep it to there for now. That water is an incredible dissolver of things. Another trippy aspect is that to at least a decent range of electromagnetic radiation, water is transparent in the range that you and I see in. It is not a coincidence that you and I see the wavelengths that you and I see, and that's because light can go through water at least many of those wavelengths. Infrared doesn't go very far through water. It's rapidly absorbed. It doesn't transmit very well or very far. UV and higher, similar, it does not transmit very well. So the reason you and I see in this, the reason bees see the way they see, the reason whales see in the color range they see in, is because of the because those wavelengths are relatively transparent to water. Okay, next, does that make sense? Any questions so far about that stuff? Excellent. You guys are incredibly talkative today. That's good. Okay, next let's talk about the composition of seawater. So first and foremost, when we talk about what's in the ocean, is all this water that we've just been talking about. So the largest thing is, of course, the dihydrogen oxide. The next most abundant stuff would be what we would call suspended material. Suspended materials is just a random name for something. We picked a value. And the value that's accepted by most people is about 0.45 microns. If something is bigger than that, as you can sort of see, right, a fleck of something, a speck of something, a board that fell off a boat, that stuff would all be what we would call suspended materials. Big stuff. Realize that the chemistry is happening to everything. It's a continuous spectrum, but we just needed to have a category. So if it's bigger than 0.45 microns, we say it's suspended. If it's smaller, we call that dissolved material. Of the dissolved constituents, we have what are called the globally conserved, or the major constituents in seawater. Okay, let me first make a note here. Okay, so this thing here that you guys are seeing, this is not percent, right? Our percentage symbol was created by clerks, created by guys that were accountants back in the day, before computers. And when we did all these balancing of ledgers and accounting of the books and balancing of the books by hand. And so, proportion is obviously a useful thing. What proportion of our money do we have available to buy rice or this or that? But these guys got tired of writing blank / over 100. So they decided to make a shorthand. So they dropped the 10. Right? So they used to say, 1 out of 100, right? So that was also 1%. So what these guys did was they just turned that into the percentage symbol that you and I know, right? They stuck a 0 on the top of the line and they deleted a 10. So we continue that same convention. It's just that you guys don't typically see that. So what I'm showing you right here, this is not a part per 100, this is a part per 1,000, right? But the same thing. We've just cut off the 10. So when you see this, just please note that's not percentage. Parts per 1,000 is being represented. Now, you can either write that as I've written it. There's a symbol for that you guys could get if you guys are typing it up. Or you can just write it out by hand that way. Or you can write PPT for parts per 1,000. They all mean the same thing, and it's whatever is most convenient for you guys in terms of your note-taking, etc. Okay, back to where was I? Okay, so we have a group of substances that are globally conserved. By globally conserved, we mean they don't change. I mean, they might change a little teeny bit, but they pretty much don't change based on where we are on the planet. Where we are in the ocean, I should say. Sorry. So we have the largest is chlorine, followed by sodium, and then we start getting into, and those are sodium. So obviously salt water, sodium chloride, right? That's the largest thing. That's why salt water tastes salty to us. And then we start getting into other guys that we would not yet call trace, but are less abundant. So realize, let's take the sodium example here. So this is not, just again to be clear, this is not 10 or is not 10.7% of sodium, right? Of the amount of the seawater we have in our hand, let's say, or the amount of the molecule. So if I have a cup of water, it's not 10%. If I have a cup of salt water, I should say, it's not 10.7% sodium. It is 1.07% sodium. Cool? All right. That's the major stuff. Globally conserved. It's basically the same if we're off of the ocean near China, if we're off the ocean near Russia, if we're off the ocean of, Somalia, wherever. Next, we have minor and so-called trace constituents, and there's a gazillion of them. So just about every element is sort of hiding here and there in the ocean. The next major category you need to know about are nutrients. So these are substances that specifically limit the growth of many organisms. In this case, we're primarily talking about photosynthetic organisms. And the biggest player here would be plankton, phytoplankton. So realize that the nutrients here, the concentrations in any chunk of the ocean we're talking about, vary widely. They are not globally conserved. They vary dramatically depending on if we're up near near a coastline, or in the tropics, or down in the polar regions, or what have you. And what we're talking about here is again, we've gone from the most abundant thing at the top of my slide here down to the things that are less and less in terms of the amount of molecules, and now we're into the tens of parts per million. So very, very trace. These nutrients again are all needed to convert light or other chemical energy into usable sugars, basically. And so the big Yeah, so I'll just say it. So this is what you guys would think of: nitrates, nitrites, ammonia, phosphates, and then something that you guys aren't that familiar with on land. This is basically glass. But silica is really, really important to a lot of phytoplankton that don't make their shells out of calcium, but make their shells out of glass. So we'll talk about those guys. Next, we have gases, actual gas molecules dissolved in seawater. And this is what fish breathe, right? So fish need an aerobic environment. They need oxygen to do the stuff they do. And they get it by essentially sucking out the little teeny pieces of gas floating around in the water. And what I have here is a comparison of how much of the particular thing we're talking about is made up of these different constituents: nitrogen, oxygen, carbon dioxide. So our air is mostly nitrogen. So the atmosphere in this room right now is mostly nitrogen. The rest of which is oxygen that you and I breathe, and then a very small amount is carbon dioxide, for example. Have a look at what happens here in surface waters. Surface waters actually have more, in terms of proportional basis, they have more oxygen than they have nitrogen. And yeah, okay, so I'll say that, and then we'll hold that for later. And then the last is we'll just have organic stuff, dead things dissolved in the water. So dead carbon molecules, rotting fish, pieces of fish, and jazz like that. Little, obviously small pieces, because we're not talking about suspended material, but organic stuff. You see this most clearly near the mouths of rivers that have a lot of organics that have washed into them from, say, like the Amazon. You have a lot of tannins and things like that. But that's seawater. Cool? Questions about what's in seawater? Everybody cool with this? Again, this sounds sort of more basic chemistry and physics, which it is, but these all have strong implications for how organisms and critters are distributed across the planet and ultimately play into various management decisions. Okay, let's talk about salinity. By salinity, we're talking about how many inorganic salts are dissolved in a particular volume of water. As I said before, the typical unit we use to discuss salinity is parts per thousand. Most places are around 34 or 35 parts per thousand. Again, just to make sure we're all on the same page, that 35, if it was 35 parts per thousand, that's 3.5% by weight is salt, and 96.5% would be water. This does vary slightly. Depends on where we are. Depends if we're near the mouth of a river, or depends on if we're in the tropics or something like that. But it's pretty close to around 35. It definitely varies, and it varies consistently, but it doesn't have massive swings. And those differences are real. A little bit of difference here has strong effects, but it's still relatively consistent. So here are some of the outlier areas in terms of salinity. Obviously, right at the mouths of rivers or in estuaries or near the poles are where they are. But let's look at an example. So the Red Sea is incredibly salty. 40 to 42 parts per thousand. Has anybody been to the Great Salt Lake? Have you ever tried to swim in it?
Yeah, the brine shrimp everywhere.
Right, brine shrimp all over the place. And could you dive down to the bottom very easily?
I didn't try to dive. It was kind of gross. I didn't want to put my
The
finger
Great
in.
Salt Lake is pretty
I was like a
nasty.
kid,
I agree.
but
I agree.
I was trying to float and everything, and it was easy to float.
You're like a cork, right?
Yeah.
Like a cork, because the Great Salt Lake it gets its name because it is so salty. It's hypersaline. And so things that you and we don't change. I mean, I might eat some more cheeseburgers or something, get a little fatter or something, but basically I'm what I weigh, right? And I can go jump in a freshwater lake, and it'll be maybe a little bit hard to stay to the surface, but not that hard, because I have a lot of salt in me. I have a lot of things that make me a little bit lighter, right? Less dense than the water. If I jump in the ocean, the ocean is denser, right? So I appear even less dense. And as that salinity gets saltier and saltier, like the Great Salt Lake, I get even, in effect, more buoyant. So it's really, really hard to dive down. So if we had, let's say I put on a weight belt that would counteract my belly and bring me down underwater, if I took that same weight that worked here off, let's say, diving the Channel Islands, and I went to the Great Salt Lake, wouldn't work. Wouldn't be able to dive. I need to get more weight to bring me down underwater. So in Finland we get some areas because in Finland's case there's so many glaciers melting, and this fresh water is this constant year-round flushing into the nearshore ocean. There we get a very fresh system. It's almost pure fresh water right near the coast. And then we get places like the Great Salt Lake, like the Dead Sea, that are just super crazy. The Dead Sea, the evaporation is insane. So whenever water comes in there, the hot sunlight beaten down, it takes that salt water and it makes it vibrate, like we were just talking about. That heat converts that liquid water into gaseous water, and the H2O goes away into the air. The salts are left behind. So we have this concentration, this buildup of salt, and so the water that is there is super salty. We measured this. If Paul was here, we could have pulled out and we'd finished moving by now. We could pull this out. Maybe we'll do this later in the semester. We could show you guys how we measure salinity, and we go to do some of our field trips. I'll definitely bring at least some of these things. There's a couple different ways we do that. We can use the specific gravity, which basically means taking a weight, a calibrated weight thing, and putting it in the water and see how it floats. We can pass an electrical current through water and look at the voltage change between those two poles. And the more easily the more readily the electricity flows through that, the more salt is in the water, basically. Or we could use what's called a refractometer, and that actually tells us how salty it is based on how bendy the light gets, how much refraction happens. Again, with the idea that fresh water refracts light at a certain amount, as we have more particles, substances, more things dissolved in the water, we get the light bends more and more. And the refractometer is awesome. I love it. Needs no batteries. So they're kind of expensive. They're like $200 or so, but it'll work for a century with no batteries. It's a pretty amazing invention. It's just got a little prism, a little piece of glass, and it looks like a little telescope. You hold it up to the light, and it's got some calibrated lines in there. Anybody know who invented that? Anybody know what BRIX is? B-R-I-X? Nobody here brews beer, I can tell that. So BRIX is the same thing as salinity, but it's just sugar. So BRIX is how sugary a liquid is. And so people that do alcohol fermentation need to know that, right? Because we throw sugar in, and that sugar, yeast ferments sugar, and that one of the products is alcohol, and then you youngins like that. So actually, they were looking for a way to standardize it, and the guys that did it were the Guinness beer people. And they realized that because they're like, this is back in the day, right? It was like, man, how do we measure this? This is hard. Some vats of beer come out great, others come out crappily, and they wanted to standardize production. And so they're the ones that first invented a refractometer. The first refractometer was to measure sugar in liquid, and then oceanographers rapidly figured out, we can do the same thing with salt. So that's what gave us the birth of the modern refractometer, to measure salinity. Okay. Interactivity time. This is way too passive a lecture for me. Okay, so the question is, why is the ocean salty?
It's from all of the runoff and stuff that comes from the land and stuff that comes from the rock.
Okay, great. So this is Lavoisier. He's a French guy that sometimes people refer to as the father of modern chemistry, and he first described the salty oceans as the reason that they are salty is just what That was a good explanation. They're the rinsings of the earth. So the water is rushing off of things. There's some salt on a rock, let's say. The water that we now know is the universal solvent is running over that rock, dissolving that salt, holding that salt in its liquid mass, and then that mass is gravity pulled down, 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 eventually gets to the ocean. Okay. All right, that seems to make sense, right? I'll ask it here. Okay, so why isn't the ocean getting saltier then? Right? So, I mean, that all makes sense, right? Totally. I can see that. We have some rocks that have some salt in them. It rains, the salt gets out. But then eventually there's going to be an earthquake. Eventually there's going to be some, we could also add the volcanic inputs, right? The volcanic inputs there might be some materials down in the bottom of the earth, and they get barfed out when a volcano erupts, and that can eventually get in the ocean as well. So those things are going on. We got it. But there's always volcano. There's maybe another volcano next week. Or there's another earthquake that exposes another chunk of rock, right? And it's going to rain. In a couple weeks, it's going to rain hard. It's going to rain on that chunk of rock. How come the ocean isn't getting saltier? Currents. Okay, well, would that really work? So walk me through how currents would make it.
It mixes things up. So when you have like a glacier or something that's inputting fresh water, it's going to mix it up.
Okay. So Aspen saying.
Yes.
No, it's good. So Aspen saying, okay, maybe we had the earthquake off of California, and we rinsed California, and then there's salt off of California. And she's saying, oh, the currents are going to mix it around. Okay, sure. But there isn't a part of the ocean that's 1,000 parts per thousand. Right, of sodium, let's say, right? So good guess, but that doesn't take us to where we want to be.
Is the saltiness somehow being used up by something?
Excellent idea. The saltiness is being used up by something. What might use up the saltiness or the dissolved constituents? What's that?
Microorganisms?
Yes, that's the answer. So here's the system we have, right? So this is what we just were talking about. Here's the ocean. We have rain and other forms of precipitation, dissolving things, rinsing the earth into the ocean. We have volcanic inputs that might not technically be rinsed, but might just be barfing into the ocean, let's say. That's a technical term. And other stuff. But it's all trapped in there. And what happens is... wow, what happened? Look at our new screen. Sorry about that. My new screen has shifted my graphics. Man, now I got to go through and check all my slides. That's embarrassing. I'm sorry. I've dropped my saltier or something here. In any event, we have what is referred to as the steady state hypothesis of these salts and major constituents in the ocean, which is that we're at roughly, of course there's going to be some variance near the sources or the sinks, but generally we have this more or less steady state nature of these major constituents in the global ocean. So salts are removed from seawater at essentially the same rate that they're added. So you're right, we are constantly adding more salt, more salt, more salt. But something is taking that salt out at more or less the same rate, at a so-called steady state. And that is this. That's life is doing that. Primarily, photosynthetic critters. So this map that I'm showing you represents are all these different deposits from around the world. So we're looking at the sediments at the bottom of the ocean. Now this isn't exact. This is sort of, this is krieged and everything, but it's generally speaking it's correct. So we've dropped down to the bottom of the ocean. We've taken a big pooper scooper and scooped up, that's also a technical term, and scooped up the sediment. And we brought it up and checked it out. And this is what we see. We see the castings, if you will, the remnants, the dead skeletons, if you will, of different groups of photosynthetic critters. So here we go. So in this orange, orange, is that orange? I don't know, tannish area, we have clays. But then, and so that would be something that's not, in other words, that's more abiotic sediments dominate. But then look, we have some things that are in, let's say, the tropics, and in this case are hugging the western side of continents, the eastern side of ocean basins. That probably has something to do with ocean circulation patterns. And what we see there, for example, are the dark green, so this is silicaceous ooze. What a cool class that I get to use the term silicaceous ooze. So this is this essentially muck that has a lot of glass, broken pieces of glass in it. That's what the silicaceous is, the silicon rich. Those are the critters that make these really killer shells of glass. Very, very beautiful critters. And so there's a couple different major groups of those. One being the radiolarians that make these sort of spheres with a gazillion million points sticking out of them. Really cool. Pincushiony kind of things. Almost like an urchin type shape thing. But microscopic. And so those guys, the radiolarians, are this dark green. But then check out down here along this front around Antarctica, we have a lot of diatoms. You guys have probably heard of diatomaceous earth. Diatomaceous earth is earth that has a bunch of deposits of dead diatoms mixed in the sediment. Then we have these, for example, these I don't know what we call it, periwinkle color stuff. And this is not silicaceous ooze, this is calcareous ooze. So this is stuff that's made up of a lot of calcium carbonates. Okay? So this is chalk. This is coral skeleton type material. And so these photosynthetic critters make calcium carbonate shells. These critters were particularly worried about with ocean acidification. More on that later. But that's changing how easy it is for these guys to make their homes, to make their bodies. And we have a lot of deposits of these guys around. Note there'll be some of these triangles here and there. These triangles are pteropods. So there's also a bunch of funky names that we might use in this class. So just to be clear, diatoms are what gave rise to this light green things. Radiolarians are what gave rise to this dark greens. Foraminifera or forams, most people will just call them forams. They'll shorten that term. They'll drop off the I and FA and put S. And then pteropods. But the pteropods, you don't pronounce the P. It's like pterodactyl. I think. Wait, is that how you spell pterodactyl? Yeah. Okay, great. Yes, I have a PhD in biology, so I obviously totally knew that. Anyway, so pteropods are totally crazy awesome. Almost all the critters we'll see in this class are totally crazy awesome. Pteropods are snails that think they can fly. So pteropods are snails that have their foot modified into wings. And so they fly around the ocean. And so a snail, you can think of your snail. Snail is a snail shell. So these guys have calcium carbonate shells. And so what we're seeing here is all of these depositions are areas that are showing consistent patterns over time, over hundreds, over thousands, over hundreds of thousands of years, millions of years, that the currents and the spinning of the earth and the winds and all this and that tend to concentrate these critters in certain areas. And so therefore when they die, they're going to sink to the bottom of the ocean, and their dead body parts are going to be incorporated into the sediment. And that dead body part raining out of the water column is the sink for these dissolved constituents. And so that's happening at essentially the same rate at which these salts and things are entering the ocean. And so that's why we have this steady state hypothesis. That's why the ocean's saltiness is basically the same as we go through time. Cool?